to the third of the Perspectives in Geometry lecture series. We're very pleased to have Graham Siegel from Oxford University, who will lecture on the general theme of quantum field theory. The second lecture is Thursday, same time, same place. The third lecture is next Tuesday, same time, same place. The fourth lecture is next Wednesday at 12 o'clock in this room. So Graham's first lecture is called What is Quantum Field Theory?
Well, I'm very honored to be invited to give these lectures, and it's very nice to be making my second visit to Austin. I'm old enough to belong to a generation for whom having one's lecture videotaped is a little bit like having one's telephone tapped. So it makes me feel a little bit edgy. One has to try to tell the truth, I suppose. So this is meant to be a very elementary lecture from first principles. My interest in quantum field theory, at least from the point of view of these lectures, is the way in which it does give a new perspective on geometry. But really we'll only get to that properly, I think, in the last of the four lectures. So I want to begin the very beginning. So what is quantum field theory trying to do? So I think one has to start with classical physics. That means physics at the beginning of the 20th century, before relativity and quantum theory. And I want to present the picture there in a specific way. You see, the essential thing then was that people were quite confident they knew what space was. Space was given, one knew all its properties before one started doing physics. And space, so we have this classical picture. So we're given space, which is some three-dimensional Riemannian manifold. And in these lectures, I'm going to mainly think of it as being a compact Riemannian manifold, which is not the way it perhaps is. I don't know. I don't know what people thought then. And one assumed one knew what time was. And time, well, somehow that was just a one-dimensional continuum. It was just somehow a copy of the real numbers. And once one knew about that, one had an ontology. Physics told you what the world was made of. So it said that the world was made up of particles sitting at points of space, or the world at any time. So it would describe the world at each time separately. The world at any time is made up of a set of particles which are just positioned at points in this manifold M. And those particles interact by means of fields. And the fields are some kind of, think of them as smooth functions, maybe sections of some vector bundle defined on M, all of M, except maybe at the points where the particles are actually sitting. So we have this ontology, which is a functor, which takes this to something xm, which is the configurations of the world. So this is some infinite dimensional manifold. A point of this manifold is a set of points in M, particles, and some fields defined on the complement of M. Now, there are various, that's obviously an oversimplification. One should say more carefully what the fields were, and maybe there are several different kinds of particles and so on, but that doesn't matter too much. And then the state of the world at any time was given by another manifold, the tangent space of this. So the configuration and the tangent vector, which told you how the state was changing in time. And then physics, so having got that ontology, physics then clicked in and told you that there was a state, which is the state at time t lies in here. It's going to tell you how this moves. So it's going to it said that this was a symplectic manifold, that there was some structure given on this. And in other words, that the ontology said that this was a functor into a symplectic manifold determined by M. We can think of the symplectic manifold structure as being encoded in the fact that the smooth functions on this space have a Poisson bracket. So we have an additional Lie algebra structure on the smooth functions on here. And in terms of that, the way in this state moves in time is given by a one-parameter flow on this manifold, which is generated by a function, a single function, the Hamiltonian, according to the rule that if you take any function, so we have a flow which tells you how the state at time t0 changes to the state at time t0 plus t. So this is a map from ym to ym. And it's described in terms of this structure simply by saying that if you take any C infinity function on ym, the way in which it changes in time is given by this Poisson bracket. This is the encoding the symplectic structure on the manifold. So there was this straightforward account. There was an ontology, and then there was this theory of dynamical systems. Well, then there were two things happened to disrupt this, of course, at the beginning of the 20th century. The first was relativity, and the other was quantum mechanics. Well, first of all, relativity. So first of all, relativity said that we had to replace that these two things couldn't be distinguished. We had, instead of this, we had a single space-time manifold W, which wasn't given as a product in that way. Well, how does that really affect this? Well, at the first sight, not really. We ought to think of we ought to replace this manifold by the actual trajectories, because we can think of, you see, in the relativity picture, we think of the particles as being unparametrized curves moving through space-time, and the fields are defined on space-time in the complement of those curves, and the whole thing satisfies, we hope, some equations, which will tell us that this ym really can be understood as something which simply depends on the space-time. Well, it's a perhaps slightly more peculiar way of looking at it, but there's no real conceptual difficulty there, except for the following, which I want to emphasize because it's where quantum field theory begins. You see, the manifold itself is fine, and its symplectic structure is probably still fine, but the state, the point of it, is not fine at all, because remember, in the original picture we had a state at each time, and that moved. Well, now we have this static point of view, where we just have one big manifold associated to space-time, and there's a point in it, which is the evolution of the universe, and all the other points of the manifold are completely wasted, and nothing happens. You see, in order to get back to a picture like this, where you have something which, a state which is moving in time, you have to decide that you're going to slice up your space-time manifold into three-dimensional spatial slices. And it's not very plausible, really, that you can do that, at least not once you believe in general relativity and you believe that the world is full of black holes and that sort of thing. I mean, you wouldn't even really know what the topology of this supposed three-dimensional slice was meant to be. The idea that somehow, well, the whole idea of a constant time slice across the whole universe is somehow a bit implausible. But nevertheless, there's no complete conceptual impossibility in taking the classical picture over to relativity. But I'll just point out this one final feature of it, that if you want to think relativistically, because it doesn't make sense to think of the state as something that's kind of moving, the substitute for that is to say that we do know, because we are still supposing we know about space-time, the functions, maybe f, say complex-valued functions, which we have on this space, they can be classified according to somehow how they're supported. We can say, because we know the functor by which this is made out of space-time, we would know what it meant to say that f depended only on the part of w which was made out of, the part of yw which was made out of a certain region in the space-time w. So we would have some way of organizing the functions on this manifold according as which bit of space-time they were giving us information about. And that's the first crucial step from the point of view of classical physics to the point of view of quantum field theory. However, of course, the big step is not relativity, but quantum mechanics. Because quantum mechanics says that it doesn't have an ontology to begin with. It just replaces this theory of dynamical systems in the following way. So quantum theory tells us that the world is presented to us not as a manifold of states, but as some non-commutative algebra. So quantum theory first of all, non-relativistic to begin with. We replace the state space by an algebra. Let's just call it A. And it's actually important, really, that it's a topological algebra, though for the moment I won't emphasize that. And the state in here, and it's also a star algebra in the sense that there is an antilinear anti-involution like this on the algebra. Traditionally, these things are algebras of operators in Hilbert space. In fact, that's where the topology comes from. And the star is just the adjunction of operators in Hilbert space. And this gets replaced by a linear map it's a star map. In other words, doing star there corresponds to complex conjugation there. And it's positive in the sense that I won't tell you for that. Well, that tells you that the theta of something of the form A star A has to be greater than or equal to 0. Well, so you see, this gives us a rather satisfactory picture of the world, in that if we know about space, we feel we understand this description. On the other hand, quantum mechanics just says we don't have that, we have an algebra. So how do we get back to a picture of the world from that? Well, this is the basic idea, I suppose, of non-commutative geometry, that we interpret this picture by saying that this algebra A is in some sense close to a commutative algebra. Well, now that's to say that an algebra is close to another algebra. If you think about it, doesn't really make sense. You can, if you have some particular elements in the algebra, you can look at how they multiply and say that they're close to the way in which some elements in some other algebra multiply. But when you deform an algebra, normally its isomorphism type just jumps from point to point, and it doesn't make sense, for instance, to, well, we'll have some concrete examples later on. It doesn't make sense to say that one algebra is close to another algebra unless you give considerably more information. But what actually happens is that the world is kind of huge, and this algebra which defines the whole universe is meant to be some huge algebra, And what we're actually interested in is just a few elements of this algebra which take our fancy, that correspond to things which we're going to observe, which are sort of interesting to us. So in particular, there must be things, for instance, which don't change too fast in time, because we can't see things that change too fast in time. So we somehow replace this A by some smaller algebra which we're interested in, and then we say that that is, in some sense, which I'm not going to tell you just for the moment, is approximately commutative. And once we have a commutative algebra, of course, we get back to a space, because any commutative algebra you can think of as the space of complex valued functions. So these are algebras over the complex numbers, of course. So any algebra has a spectrum, at least the homomorphisms into the complex numbers, the algebra homomorphisms. If we have a commutative algebra A0, we can define a space like that, and we can think of the elements of the algebra as being functions on that set. So when you have any one of these things in any element of the algebra, you get a number. So we somehow interpret this picture by saying that A we think of as a small deformation depending on a parameter h of a commutative algebra A0, and we have this theta, the state, which is a small deformation of a homomorphism of algebras, theta naught. So we have to, it's the whole pair we have to take as being deformed by this small deformation parameter h, which is Planck's constant. And then we say, well, to good enough approximation, what we're really seeing is this, which is a space of states and a point of its spectrum. Well, of course, that still doesn't tell us about the world, because unless we have the functor which takes M to this algebra and understand something about the nature of that, we have some ontology, then we still don't have any kind of picture of the world. We just have an abstract symplectic manifold or something, and we could interpret it any way we like. I should have said, of course, the reason why this is a symplectic manifold from the point of view of quantum theory is that if you think of this thing as looking like this algebra, if you think of A0 as being the C infinity functions on Y, then this is a commutative algebra which is part of a one-parameter deformation into non-commutative algebras. If you look at the derivative of the multiplication at parameter value 0, that, of course, is a bilinear bracket operation, which is exactly the symplectic structure of the spectrum of the algebra. So at least that shows how the quantum theory, in some sense, reduces to this. Now, quantum field theory, you see, is an attempt to add ontology to quantum mechanics, in that it's meant to tell you how to get from a space-time manifold to a picture like this. Now, usually when people talk about quantum field theory, they leave it at that. Quantum field theory is the study of this step from space-time to algebra, and how we then interpret the algebra is something they don't say too much about usually in books on quantum field theory, or at least they only tell you how to calculate scattering amplitudes, which are not usually how people describe the world around them. So I would like to say something about that, because I think it's of the essence. And so in a way this is maybe baby stuff. But one of my favorite writers, one of the people I most admire really, is Freeman Dyson, who a long time ago wrote a popular book about quantum field theory. And quite right at the beginning of it, he said, and I was rather disappointed by this, and I thought quite a lot about it. He said, in quantum field theory, we have a certain mathematical structure, and that makes clear that what we actually observe are particles situated at points of space-time, or moving through space-time. But he said, unfortunately, this is something that can't be explained non-mathematically, so he's just going to take it as something given. Well, I certainly can't do any better in the sense that I don't think there's any non-mathematical explanation, but I did wonder what exactly he took to be the mathematical explanation. I mean, one can imagine lots of things. This was, of course, written a long time ago. I think it's worth saying what the mathematical structure is that makes us see particles, because that really motivates the whole way one's trying to define the structure of quantum field theory. So you see, the famous thing about quantum field theory, well, what was wrong with classical physics? You see, it sounded so good, maybe, the way I said it, but it was never able to be made intelligible because, you see, we had this infinite dimensional manifold of states which was built out of space-time, but it was a pretty peculiar manifold, really, because the fields which were defined on it, if you just think of elementary physics, clearly the electromagnetic field becomes infinite where a charged particle is sitting. So the moment you try to write down any kind of equations which tell you how the particles move under the action of the field, you get into absurdities, because the field where the particle is always infinite. So of course people tried to do things like saying, well, you subtract the contribution to the field made by the particle itself, then you get something finite, and that's the thing which makes the particle move, and so on. But that led to fairly absurd results. And in any case, the whole point of the field is that it isn't divided up into the amount of the field caused by this particle and by that particle and so on. There is just meant to be one field in which the particles sit. So there was no way, really, of making sense of this picture, this classical picture, mathematically. And when you bring in general relativity, of course, it's still worse. The equations of general relativity are certainly not compatible with point sources. They would be very bad kind of black holes or whatever in space-time. Quantum field theory, of course, improved the classical picture in the sense that it said that what is really there, if we want a classical picture of it, just consists entirely of fields. There are no particles at all. And because of this mathematical device, we actually see particles, but that's not really essential. Well, what does that really mean? Perhaps it's worth saying that it's kind of the opposite of the way in which the fields got there in the first place. Because why did people have the fields there? Well, again, this is a somewhat ahistorical way of saying it. But what the field, you see, one could have tried, and in fact people did, Dirac and Wheeler and Feynman and so on, did try to express the laws of electrodynamics in terms of completely action at a distance, taking relativity into account. So for them, the field was just summing up all you needed to know about the past history of where the particles were, so that you would be able to, at a certain time, have a complete set of data which would predict how everything was going to evolve. So, in a sense, you see, you might have just tried to make a theory which just had pure particles. And in fact, what you do is make a theory which just has waves, but then we want to understand why there is these two different ways of looking at it. Now, you see, on the face of it, because of this, obviously, given a non-commutative algebra, regarding it as a deformation of a commutative algebra is an art, not a science, and a thing can easily be, a given algebra can easily be a deformation of many different non-commutative algebras, many different commutative algebras, and so there'd be no contradiction in having saying that this non-commutative algebra approximates particles and approximates fields. So that, however, it's not quite as simple as that. And I'd like to explain the sense in which the fields are more fundamental, although what we observe is the particles. So I'd just like to say very quickly what actually happens and what this statement of Freeman-Dyson's actually is. You see, supposing, let's go back to the non-relativistic picture. So we have our space M, three-manifold. And so what are the two commutative algebras that we'd like to say look the same, or are approximations to the same non-commutative algebra? Well, you see, if we were looking at configurations of particles in here, then we would get some space, well, let's just consider the configurations. Xm would be a disjoint union for every number of particles of the configurations with n particles, and we want them to be identical, so we'll divide by the symmetric group on n letters permuting the particles. Now, this isn't quite a manifold, but I'm talking on a level of vagueness if we'll overlook that for a moment. So this is the particle description of some species of identical particles sitting in there. Now, on the other hand, we could also look at a wave description. Well, the simplest kind of wave would be just a C infinity function on M. So this is a vector space. Let's just call it V. So let's now compare the C infinity functions on X particle, the C infinity functions on the M. So do these resemble each other? Well, actually they do to some extent, in the sense that at least if this has an inner product, which might well do, just using the Riemannian structure of M, you could think of each point of Vm as giving you a linear form on Vn. So inside here, you could imagine the polynomials on those linear forms, made up from those linear forms. So the polynomial algebra of this, you can imagine, at least as a dense subalgebra of that. And that algebra certainly maps to this algebra, because when you have, supposing we have a linear form, well, supposing we have f in here, then we can associate to it the function which, to a configuration of particles, when we have n particles, x1 to xn, we take that simply to the sum of the values of f at those particles. That's a map from this to this, so we just extend it to an algebra homomorphism. So a dense subalgebra of this certainly maps to that. On the other hand, that's a bit misleading. That's not the map we want, as we'll see. However, it's worthwhile to think about this map, because you see, supposing we consider the extreme baby case where M is a point, so that's not three-dimensional, but no matter, then in this case, you see, we're just looking at this is just the real numbers, and the other space is the configuration. Well, if we allow multiplicities, x, m is just the natural numbers, just the number of particles we have sitting at this point. So we're interested in the functions on the natural numbers versus the functions on R. Well, there's clearly a restriction map. But you see, these are meant to be topological algebras. To say that we see particles is to say that this algebra is really acting through this algebra. I mean that that the the way in which this algebra is actually going to go into our algebra A, the topological algebra of observables, actually factorizes through here. In other words, if we think of the function, the identity function x, is somehow generating this, so I'm going to be rather sloppy. Let's call it f, because that's what I called it there. Then that's going to go to something over here. And what we want to say is that the spectrum of this thing f is the natural numbers and not the whole of R. You see, it's important that in this topological algebra, an element has a spectrum, and it has to have a spectrum which consists just of positive integers. It can't consist of arbitrary real numbers. That's the beginning of the fact that what we see is particles. And of course, in this case, it's known exactly what algebraic property will make that happen. So very roughly, we have the Stone von Neumann. We have the Stone von Neumann theorem, which says that if this element f is actually part of a star algebra, which is not commutative, and which contains an element phi, and is the product of two elements like this, where these things don't commute, but have commutator equal to 1. So if we have this algebraic setup, then that automatically implies this. Well, I'm saying that oversimplifiedly because I should discuss unbounded operators and where things are defined and so on. But for the moment, this will be good enough. We have this basic algebraic mechanism. Now, how does that help to give you a criterion that says in general that when we have the C infinity functions on this acting, it actually acts through this space so that we see particles? Well, you see, if we want to be able to see particles, then what we expect to see is that there should be some element fu in this algebra that we're constructing for each region u in M, such that spec of fu is always a positive integer, and it's going to be the thing which tells us how many particles are in the region u. And of course, we want this to be like a measure. We want this to add when you take the disjoint union of different u's. So, in other words, that tells you that you want then fu to be the integral over u of some operator value distribution defined on M. This will make it additive in the right way. And you want this operator value distribution to have the property that the spectrum of this thing is positive integers for each u. And at first, I think you'd immediately think that's completely inconceivable. However, there's in a sense, immediate generalization of the Stone von Neumann theorem, this theorem, which says that if you have that an operator value distribution f of x has this property, if there's another operator value distribution phi of x, such that on the one hand f of x is this, and on the other hand these things have the generalization of that commutation relation, that the commutator of these things is the delta function. So the thing which is, so this is only meant to make sense when you multiply by smooth functions of x and y and integrate. This is the delta function along the diagonal in M cross M. So this is an equation of distribution, operator value distributions on M cross M, and this is the delta function along the diagonal. So if you have this situation, then what we see is particles. Now, there are lots of problems here, because if this is an operator value distribution, we seem to be trying to multiply it by itself, and everyone knows you can't multiply distributions. It's the first thing. Well, on the other hand, we don't absolutely need it to be the product quite. What we do need is that there is a thing phi of x such as its commutator with phi of x is phi of x. Phi of xy is delta xy phi y. That is the property. Instead of having that property, it will do to have this property. So what actually happens is that inside the space of function, and this is a general fact in quantum field theory, that inside the space of functions on the space of fields, there will be some subalgebra, which in this case is strictly commutative, which has this interesting spectral property, which forces it to be the functions on a particle space. And when we ordinarily look at the world in a mood to see particles, you see we're only looking at the smaller algebra generated by these things fx. And we don't know anything about the things phi of x, although they're also in the algebra. But the fact that this algebra, completely commutative algebra generated by the fx's, is sitting inside a larger non-commutative algebra, that is the thing which is forcing us to see particles. So you see, it's the functions on the fields, the waves, which are the essential non-commutative input, which is going to force the world to be made of particles. Well, now let's see how we can actually try to encode this a little bit more precisely mathematically, what kind of structure this is leading to. You see, one of the clues is that we seem to want to say the important things were functions which just somehow pertained to a particular point of space. And we're still assuming space-time is something we know about. And we sort of would like to be able to multiply these things, but maybe there's some problems about multiplying it. So now let's talk about the traditional formulation of quantum field theory. So this is the traditional, or essentially, so we again on a space-time M, space-time W. Sorry. Well, we say for each x and w, we have a subvector space which I'll call OX, contained in the algebra which is meant to describe the universe. And this is not a subalgebra. So it's going to contain things like fx and phi x, but we aren't really going to be able to multiply things in it. And all the information about the theory is contained, you see, we will automatically have multilinear maps whenever we take n distinct points. So supposing x1 to xn are distinct in W, then of course we can multiply them together in A, And then we have this theta, remember, which was what quantum theory said was there. And so we have some maps which traditionally are written if we have an element fx1 in this one, in that one. One traditionally writes this map in some kind of expression like this on the space-time W. So we don't, and all the information is meant to be encoded in giving this presumably infinite dimensional kind of vector bundle on space-time, together with all these multilinear maps parametrized by the finite subsets of space-time. The trouble is that from that point of view, it's extremely difficult to make sense what algebraic or whatever properties you'd want those things to satisfy. Well, even more problem to make sense of the analytic assumptions you'd need to make. So we'd like to be able to pin this down, of course. But before we pin it down, I'd just make one remark. Because one of the many people, certainly including me, find the traditional Copenhagen orthodoxy of quantum mechanics extremely repellent. And one of the repellent features of it is that the world is meant to be described by this non-commutative algebra. On the other hand, the multiplication in the non-commutative algebra has no special physical significance. In fact, if you know about quantum mechanics, it's the self-adjoint elements of the algebra which represent things you can observe. The product of two self-adjoint elements is not self-adjoint in a non-commutative algebra. The commutator in the algebra plays some sort of physics role, but the product certainly doesn't. It's a very artificial kind of thing. And you notice that the advantage of this point of view is that now we no longer have an algebra. All the information is meant to be encoded in these vector spaces and these multilinear maps. So that suggests that possibly an algebra isn't actually quite the optimal way to go. I mean, maybe, obviously we don't want to try to tamper with quantum mechanics, which I think most people, as a sort of fact about the universe, believe. But we would like somehow to be able to formulate it in a way which was perhaps a little bit more intuitive. I should have said that the traditional, at least the most popular way of understanding what these things are meant to be is the sort of path integral approach, which I'm going to talk about in the next lecture, where we have a sort of mythological superstructure which this is meant to reflect. We're meant to say that associated to W, we have some space of so-called classical fields. So this is some manifold. So this is the path integral mythology now, I'm telling you. So what might these things be? Well, they might be, say, for instance, smooth real-valued functions on W, or they might be something, they might be maps from W into some auxiliary Riemannian manifold. That's what you call a sigma model. Or they might be a point of this, in real physics, this is always the space of isomorphism classes of some category. So if you, in real physics, what this space is it's the space of vector bundles with some structure group on W, together with a connection in that vector bundle and a cross-section of the vector bundle. So that would be what this space is in the standard model of particle physics. And the situation is meant to be described by an action functional which is meant to somehow, well, I'll give you some we'll talk about examples of it another time. And out of these things, we're meant to somehow produce a measure on this space, which is traditionally written h being Planck's constant. So the complex valued measure on these classical fields. And the space O of x is meant to be the functions supported in the infinitesimal neighborhood of x. So what does that mean? You see, one of these fields are meant to be some things which are locally defined. Essentially, they're functions on W. So to say that a thing is supported in the neighborhood of x, that means that the value of this function on a field is meant to depend only on the value of the field and on its derivatives up to any order at that point. So these are this is contained in the C infinity functions on the space of fields. And the mythology says that this thing is meant to be the integral over all the fields of f x1 phi, f x2 phi, f xn phi, d mu phi. It's the, so to speak, expectation or correlation function of these complex valued functions with respect to that measure. Now that it's only in a number of very special situations, like certainly when W has dimension at most 2, that one can make any sense at all out of this measure. It's only when, in the case where W is one-dimensional and we have Wiener measure, that you can really honestly make sense of this as a measure. But this idea that everything is determined by an action functional is certainly the underpinning of all of quantum field theory. So, and one of the things which I should mention, because right at the beginning, I suppose, because it does in a way seem rather, well, perhaps I'll leave that as things are getting a bit late. I'll just say the typical kinds of examples are when, for instance, phi of W is the C infinity maps from W into some given fixed target manifold, Riemannian manifold Z. And a typical example of such an S would be the function whose critical points are the harmonic maps from this Riemannian manifold to that Riemannian manifold. So half the integral of the derivative taken with respect to the covariant derivatives and so on in here. This is what mathematicians call the action of a map between Riemannian manifolds. And this would be a typical example of such a function. One of the things that is very striking, that makes one think this picture can't be completely crazy, is that it's very difficult, if you propose a situation of this kind and try to associate to it a quantum field theory, it's usually impossible to do and certainly usually extremely difficult to do. But the thing that's striking is that the difficulties and the possibilities of constructing the quantum field theory exactly correspond to the goodness or badness of this function S from the point of view of calculus of variations. In other words, if I said that this works beautifully when W is one-dimensional, and there a harmonic map is a geodesic, and we know there's a beautiful calculus of variation for geodesics, Morse theory, and that corresponds to the fact that there's a beautiful Wiener measure which solves this problem when W is one-dimensional. If W is two-dimensional, we have, for instance, two-dimensional Yang-Mills theory, which again has a beautiful variational theory and a beautiful quantum field theory. On the other hand, if we have this example of mapping something two-dimensional into a Riemannian manifold, then we know that calculus of variations is on the edge there, that you can almost use calculus of variation, but there's the phenomenon of bubbling when you try to pull a map tight in the sense of the energy. And that corresponds to the subtleties of conformal field theory, which certainly exists in two dimensions. On the other hand, if you tried to do this when W was three-dimensional, then everything goes wrong. If you start a map of something three-dimensional into another manifold and try to reduce its energy, then the map just cavitates. The moment you try to flow downwards, the map just becomes hopelessly discontinuous, like a fishing net. It's like trying to flow backwards in the heat flow. If you have a smooth function and you try to move it backwards in the heat flow, it just disintegrates. So, and that similarly corresponds to the fact that you can't define a sigma model in three dimensions in quantum field theory. Well, I now want to propose a kind of formulation. You see, this picture is so suggestive, one would like to try to retain some features of it while not banging one's head against the apparently intractable problem of trying to define an actual measure on these spaces of fields. And so I'm going to pursue the following attempt to incorporate at least one feature of that. So what feature do I want to incorporate? Well, you see, the main idea in this picture is that these classical fields were locally defined on W. In other words, to say what a field is, you need to, it's something which you give in the neighborhood of each point of W. It'll have to be globally smooth or something, but it's like a kind of section of a sheaf defined on W. And this action functional is also local in the sense that if you write W as W1 union W2, where these intersect on some codimension 1 manifold M. So I'm thinking of W usually as being a compact manifold, closed manifold. Imagine we divide it into two along some submanifold M. Then this is meant to be local in the sense that S of phi being the field on this, is simply the sum of S of phi restricted to W1 plus S of phi restricted to W2. That the amount of action is just the sum of the contributions from each piece. Now that might make you think that the measure on phi W, well, phi W somehow maps to phi W1 plus phi W2 by restriction, because the fields are local. But the trouble is, I was thinking of this as a closed manifold, and these are manifolds with boundary. So it's a little bit dubious what this is, except that in some schematic sense, this should be isomorphic to pairs of fields which agree on the intersection. So assuming you could restrict a field to here, this interface, a pair of fields which agree ought to be exactly an element of this. So we have a measure here. Well, the question is it just come from a measure on the two pieces? Can you integrate separately? Well, of course, if you could, then physics would be very uninteresting, because it would tell you that the two halves of the world were statistically independent, were uncorrelated, that nothing here ever affected anything in there, and that would be a very dull universe. So this can't be true, but the point is that this S depends not just on, it's not just the integral of a function of phi, but it usually involves derivatives of phi, which tell you that at the interface, these things have to have their derivatives agreeing too. In other words, this integral, which we write schematically like this, you shouldn't think of as a product. Sorry, that should have been a phi. Sorry, I'm terribly sorry. That should have been a phi. Phi in phi w. Sorry. Terribly sorry for that. That would have been very misleading if anyone thought it was a point of w. This thing, which looks somehow as if it's meant to be a product of measures, one for each point of w, actually introduces correlations between the distribution of probability at nearby, infinitesimally nearby points, and that's the way the information transmits. So the axiom that would, well, the way that's encoded in this picture is what we're going to hope for is to say that associated to a manifold with boundary, like W1, we're going to have a measure d mu1, which takes its value, will be a measure with values in a vector space, usually a Hilbert space, Hm associated to M. And the way in which this is reflected is that the measure for the whole space, which is meant to be a kind of scalar measure, should be the pairing of two measures where this is an inner product in some vector space associated to the cut. And the size of this vector space measures the way in the amount of, it's the channel by which information is transmitted between those two regions of space-time. So we want to try and axiomatize that, and the thing which I've now said sufficiently often that I got very bored with it is, so we'll give now a formal definition of a d-dimensional quantum field theory. And this is really only, this is a kind of sketchy and rather provisional definition. I'll comment on that later on. So it's going to consist of the following data. First part is to each d-1 compact oriented Riemannian d-1 manifold M, assign a topological vector space Hm, and secondly, to each compact cobordism of course oriented W from M0 to M1, associate a linear operator I'll call U of W from H M0 to H M1. Now, and we want, I'll sort of try and make that a little bit, pin that down a little bit more narrowly in a second, but basically we want just two properties. So thinking of this cobordism M0, M1, and a piece of space-time W intervening between them like that. And this is meant to have some Riemannian or Lorentzian structure. I'll come back to that in a second. But the two crucial axioms are meant to be first of all, disjoint union goes to tensor product, so I'll just call that tensoring. In other words, H of a disjoint union of two manifolds is going to be the tensor product in some appropriate sense of topological vector spaces like that. And similarly, if you took the disjoint union of two cobordisms similarly, and secondly, the property which I'll call concatenation which just says that if you take two cobordisms and string them together, then U of the union is the composite operator. So a sort of functoriality property. And they're the only properties. Now, I need to comment. I'm going to stop fairly soon. So I want to say a few comments and then tell you what's going to be in the other lectures, because I want to develop this picture. So the first comment is this doesn't make sense for one very obvious reason, that when you want to sew two cobordisms together, these are meant to be smooth manifolds. If you just have the two manifolds and you know how to identify their boundaries, you don't know what you mean by a smooth function on the union unless you specify. So you need some additional data here. So what this M really has to be is that this is actually a germ of a D manifold along M. In other words, M is a D minus one dimensional manifold, but what we're really thinking of is a very thin neighborhood of it, which is actually a D-dimensional manifold. And when I say it's a germ, what I mean is that we identify two of these things if one is contained in the other, and so we identify any neighborhood of the thing we started with any smaller neighborhood. So but basically this has an infinitesimal thickening. So that means that the second axiom, the concatenation axiom, is at least well defined. The next thing to say is we want to discuss, so I'll say more about the implications of that later on. The next thing is what kind of topological vector space. I'll say a little bit more about that in the second lecture, and what kind of tensor products and so on. The much more interesting thing to say, and that's really the most interesting thing I think in the next lecture, is going to be the discussion of something I've so far swept under the carpet, which is the subject of Wick rotation. Let's go back just to this picture. Space-time is presumably some Lorentzian manifold. It has an indefinite inner product on its tangent spaces, which on these spatial slices we think of as being proper Riemannian manifolds. Now, on the other hand, the fact that energy in physics is positive is encoded in the fact that when you have this operator defined for a Lorentzian manifold, you can perform some kind of analytic continuation, what's called Wick rotation, so that this becomes a Riemannian manifold. Now, I want to discuss that somewhat geometrically in the next lecture. But so what really is going to happen is that the structure on this W, this will have a complex Riemannian structure. In other words, there'll be a complex valued inner product on the tangent space at each point. And it won't be arbitrary, but it will lie in some complex domain in the space of inner products. So it will, roughly, this is not quite right, you want its real part to be positive definite or something like that. That's not quite the condition. I'll explain it better. But there's some domain in the space of complex structures which contains the honest Riemannian matrix on W in its interior as a sort of real slice, and contains the Lorentzian matrix on its boundary. And positivity of energy is encoded in the fact that this is defined for cobordisms with all of these, any of these complex metrics, but it's holomorphic in the complex metric, so it's completely determined by what happens on Riemannian metrics. And on Riemannian metrics, this is actually going to be a trace class operator, so a very strongly contracting operator. On the other hand, when you move to the boundary of the region and you get into the Minkowskian metrics, this will no longer be a contracting operator. It will be something more like a unitary operator. In other words, what I have in mind is that if, for instance, on a Hilbert space, you have a one-parameter semigroup generated by a self-adjoint operator H, so H is just a self-adjoint operator probably unbounded in a Hilbert space, then to say that the spectrum of H is positive, so it has a spectrum on the real axis, so the spectrum of H is contained in R+, that's equivalent to saying that this is the boundary value, is defined for T in the upper half plane, and in the interior, a contraction operator in the interior. You see, you think of this kind of operator as being associated to a Lorentzian manifold of length T. You think of E to the minus HT, a contraction operator, if this has positive spectrum, as associated to the Wick rotated thing, which you can think of as having length IT. So we want to make sense of this simple picture for higher dimensional manifolds. Well, that's one of the things in the second lecture. Now the next thing. So in the third lecture, I want to discuss the fact that this is rather obviously not an adequate, although this is a very simple axiomatization, and I want to talk about some of its advantages. It has some obvious faults in that it's only partly encoded the locality of quantum field theory. And the best way to see that is that in this axiom system, we simply associated to an d-1 dimensional manifold of vector space, but one immediately can ask the question, supposing M itself is cut into two, M1 and M2, by some codimension d-2 dimensional manifold N, is there some way of making HM in some sense out of some data associated? I'll put a star to indicate that one doesn't know quite what it was. one feels one should have some formula like that, that there should be some data associated to the two halves out of which one can recapture that. So that's going to be essentially the subject of the third lecture. And to end today's lecture, let me explain why this does give us something like what we would expect. Why does this give us the traditional formulation of quantum field theory? Well, you see, supposing you have a space-time W, and we want to get from this setup the data that I had before. So we have a point x in space-time. We can consider little neighborhoods of it. Let's consider a neighborhood U. Well, let's call it D. Think of it as a little ball with x in its interior, but not necessarily a Riemannian ball. Then we can look at the boundary of D, and we can look at the vector space when we have such a theory associated to that. Now, if we take two different small balls, D and D prime, both with x in the interior, we can order these things by inclusion. D is contained in D prime. In that case, what is between the two things is a cobordism, and would give us a map. Our theory would give us a map. I want to give it from D to D prime, that way. So I'll think of them as going outwards. Obviously, it depends which way you choose the orientation, which way the cobordism goes. So we have this U associated to D prime minus D interior. So we have an inverse system of topological vector spaces indexed by the balls containing x in the interior, and we simply define OX to be the inverse limit in the sense of topological vector spaces of these things, where D runs through that inverse system of neighborhoods. So that's a vector space associated to OX. Where do we get these maps, which we said we wanted? Well, you see, if we, let me just redraw that picture. We have W, we have some points x1, x2, up to xn. Well, we put a little neighborhood around each of them. Well, supposing W naught is W minus the union of the interiors of these disks. So we just take out all of those things. That's a cobordism from the disjoint union of the boundary of the DIs to the empty set, if W is a closed manifold. So it gives you, by our axioms, a map from H, boundary of D1, tensor H, boundary of Dn, to H of the empty manifold. But this tensoring axiom says that H of the empty manifold is the complex numbers. So we get a multilinear map like that. For each choice of disjoint neighborhoods, it's obviously compatible by the concatenation property with inverse limits. So we therefore can take the inverse limit and we will get the map like that. So at least we recapture the traditional data from the setup that I gave you. Well, I think I'll just say one more thing. So the last of my lectures will be not really about quantum field theory at all, but about non-commutative geometry. Because this picture, what does it really tell us? You see, supposing I said these things were vector spaces, they weren't algebras, but supposing we just take a disk and consider a point x at its boundary. So this is a standard Riemannian ball, and x is its midpoint. Well, of course, we have O of x mapping, because of the definition, to the boundary of the disk. And you should think of this being an inverse limit of this thing. You should think of this as being some kind of completion of that. You see, it's like sort of thinking of C infinity functions as the inverse limit of k times differentiable functions or something. So think of these as the k times differentiable functions, and these as the C infinity functions. Now, suppose we now take some other points, x1 up to xk, anywhere in the disk, but disjoint, and then put little balls around them. We'll then have a cobordism from the union of the boundaries of those things to this. So we'll have a cobordism from the disjoint union of the boundary of the little di's to the boundary of D. And hence we'll, passing to inverse limits, we'll get a map like this. So what you see is that although these things are vector spaces and not algebras, they have a nearly defined algebra structure, in that if you pick a number of points close together, I chose k points now, then for each way of putting k points in a disk, you have a sort of way of multiplying which takes values not in O at the midpoint, but in some completion of it. So it's some not too well-defined multiplication. In fact, a family of multiplications parametrized by the distinct k-tuples in the disk. So this is a sort of more subtle kind of thing than an algebra. It's a sort of algebra up to homotopy, in a sense that's become very fashionable, of course, in many quarters recently. And somehow this is the basic structure which quantum field theory finds automatically, and which supersedes the need for the algebra structure in ordinary quantum mechanics. Now, and you can think of course, it's a program now mainly associated with the name of Kontsevich. You can think of quantum field theories as a way of formulating, of describing non-commutative geometry quite apart from any physical application, and it's interesting to pursue that. That's what I'll be doing in my last